continue with our nuclear chemistry discussion with the next section in your textbook, which is section 20.3, that reviews natural radioactive decay. So you may not know this, but there are many, naturally radioactive elements that surround us, whether it's in our soil, our water, etc., even in bananas. There is the radioactive potassium-40 isotope. If you were to use this thing called a Geiger counter and place it near a banana, it would register that there is radioactivity present. So all these nuclei that we discussed before that lie outside of the belt of stability or have more than 83 protons tend to be unstable. This results in the spontaneous emission of particles such as alpha or beta particles, or electromagnetic radiation such as gamma emission. This again is to create a more stable nucleus, so that when unstable nuclei disintegrate, this might not occur in just one step, but rather it's the start of what we call a radioactive decay series. So a new term to define until it reaches a stable isotope. So let's look at the radioactive decay series for the isotope uranium-238. So uranium-238 goes through 14 steps in its decay series. This is shown below here. So we start with uranium-238. It undergoes alpha decay, and at this point, this is the half-life of uranium-238 isotope, about 4.5 billion years. So it takes quite a while for uranium to radioactively decay. But this is, step 1 in our 14 steps. We then see that there is thorium-234 created. That goes through beta decay. The half-life for that is only 24.1 days. So that's how you can interpret this radioactive decay series that's found in your textbook. You have the parent, then the daughter. Each of these 14 steps. This is step 2, 3, etc. We get to polonium-214 down here. We see that there's 2 different paths that our decay could take. So majority undergoes alpha decay, but some small amount, 0.04% of this polonium, would undergo beta emission. We follow along and notice here we actually have a lead isotope, different isotope here, but both turn back into bismuth-214. And eventually we get a different isotope of lead, lead-210, another isotope of bismuth, then after another beta decay. And finally, after all of these, 14 different decays occur, we end up with a stable isotope, which is lead-206. So that is an example of a naturally occurring decay that happens in a series of steps. So we discussed before, each of these individual steps is an alpha or beta decay, and we have the parent, then the product is called the daughter. That brings us to a discussion of the kinetics of radioactive decays. If you recall from earlier chapter 14, we reviewed kinetics, or how fast reactions occur, rates of reactions, and all radioactive decay, key for us, right, follows first order kinetics. So there's going to be an equation that we'll see down below here that relates that, and rate of decay is really just some constant value k, rate, first order rate constant, same as we looked at previously in chapter 14, same K. And then we have N listed here. Instead of a concentration like we saw before, we're going to discuss the number and for number of radioactive nuclei present at our start time, time t. So we want to know after a certain amount of time passes, how much would be left. So we have radioactive nuclei time 0, then at the end of our reaction time t. So if you remember the equation that was given earlier in Chem 2, have the natural log of this would be our analyte at time t, so concentration at time t was equal to the negative rate constant k times the time that has elapsed plus the natural log of, and here we're going to call it initial n sub 0, but previously it was concentration a sub 0. So this is the same equation here, just rearranged. Whenever we divide by a natural log, it would look like this here. I'm sorry, subtract a natural log, we write it this way. So this is really an expanded form, natural log of n sub t minus natural log of n sub 0. It takes this form here. So let's utilize this equation with some examples below here to find out, in this example, how much plutonium-239 will remain after some time. So we have 1,000 years, 25,000 years, or 100,000 years. So to rewrite our equation here, this natural log of nt over n0 gives us percentage that remains, right? The amount at time t divided by the starting amount will give us our percent remaining. This is equal to negative k. So 1,000 years, we would do negative 2.88 times 10 to the negative 5th per year. That's our k value, our rate constant. Then we multiply that by 1,000. This natural log of nt over n0 is going to be equal to negative 0.0288. Now, if you remember, or would like to know how to get rid of a natural log, we raise it, we take the e of it, right? E to the natural log, cancel that out. So we're going to raise this number to the negative 0.0288. And when we do that, we get this value here, 0.97, some other numbers. But this is the decimal form of our answer, which we multiply that by 100 to get 97% would be remaining. Let's look at that again, but with a different amount of time that passes. So we're going to have natural log of nt over n0, same rate constant, so negative 2.88 times 10 to the negative 5th per year. Again, this is, in a year, this much would decay of our starting amount. So after 25,000 years, we end up with negative 0.72. When we raise that, we take e to the negative 0.72. Let's plug that in. Get 0.4867. Which we only need 2 sig figs here. We can say about 49% remains. All right, so our last example here, change colors again, and we have n sub t over n sub 0 equals that same rate constant, negative 2.88 times 10 to the negative 5th per year. Now we have times 100,000. So this would give us negative 2.88 raised to the negative 2.88. Let's do that. And we find that we get a decimal of 0.0561. And we multiply that by 100, and we see that only 5.6% remain of our plutonium-239 after 100,000 years. So quite a bit of time has passed, and there's still some of this parent nuclide, this plutonium-239 isotope remaining. Remember how to do that for, again, your homework or for the exam coming up. Let's look at one other equation that you should know. This is the half-life equation. So we're going to look at mercury 197. It's a radioisotope that's medical use for kidney scans, right? So they inject this isotope or you consume this isotope somehow, and it helps doctors identify, problems with the kidney. So we're given our decay constant, our rate constant here, K equals 1.08 to the negative 2 per hour. And we want to know what is the half-life of mercury 197. So we're going to use this equation up top here, and we're just going to plug in values. So this is derived from the natural log of 2 here. So if you plugged into your calculator natural log of 2, you'll get this value, this 0.693 value. You can skip that step and just say 0.693 divided by our rate constant. So that would be 0.693 divided by 1.08 the negative 2. And do that, we find out this would equal about 64.2 hours. So this is the half-life for this isotope of mercury, this mercury 197. Now let's look at this next example. We're going to take sodium-24. It's another radioactive radioisotope that's used medically in studies in the blood. So they would inject this into your blood, and would highlight certain things that our doctors are looking for. So we want to know what's the half-life of this sodium-24. And you should know that half-life is important with these medically used radioisotopes because we don't want to keep radioactive stuff in our system longer than we have to. So let's see how long this sodium would last in your body. So we would then do this, t to the 1/2 equals 0.693, or natural log of 2. And then we divide by K, our 4.63, the negative 2 per hour. So now our value is going to be in hours. Again, we have 0.693 divided by 0.63 to the negative 2. We get 14.967, or we could say approximately 15 hours. And if we wanted this other value in days here, if we were asked for days, we would divide by 24. And 2.67 days, or let's say 2.7 days. This is less than a day, so we probably wouldn't be asked to find the half-life in days for the sodium isotope. So that's everything for this section on naturally occurring radioactive decay, and the two equations that you should note for, again, your homework or exams. We are going to skip part of this section. That's the radioactive decay dating. So they use a certain isotope of carbon 14, to date things based on organic things, rather, living things can be used, can be dated using carbon-14, and then other elements, uranium, ratios are used to date things like geological things like rocks. But we're going to skip this section. You will not be responsible. This is not on the exam. So next time we'll pick up with section 20.4, and that is on nuclear transmutations.